Welcome, UC's contestants. Welcome, everyone. Hello, we are really excited to have this plenary talk uh, today. Before that, I hope that the interviews are going well. After some technical problems, please, we apologize about that, but I'm sure everything will go okay. We are really excited about the excellent projects we are presenting in this UC's Salamanca. Okay, so we have really the honor to have here with us online an excellent physicist, an excellent communicator, and a Nobel Prize laureate. It's really an honor. Hi Bill Phillips.
It's good to be here.
Okay, so Bill Phillips, she's a Nobel laureate in physics in 1997. He shared the Nobel Prize for development of methods to cool and trap atoms with laser light. Okay, he works in the National Institute of Standards and Technology, and he will present today a talk which we are really excited about. It's a talk about a new measure, the quantum reform of the international system of units. And I particularly like this talk because it's really transverse to all the topics in science. One of the great things of UCIS is that we have many topics, all the topics are covered, and this talk is really transverse to all those topics. So I don't want to spend more time talking, so I will give you floor, Bill. Thanks for much. Thank you so much for being with us here today, and the floor is yours.
Well, thank you very much, Carlos. It's a pleasure to be here with you, albeit virtually. It would be great if we could all be in Salamanca together and enjoy the wonders of that city and have the chance to really talk with each other. But this is the best we can do under the circumstances, and I'm happy, especially to be talking to all of these young people. So, I come from a place called the National Institute of Standards and Technology. It is the National Metrology Institute of the United States of America. Every major country has a National Metrology Institute, someplace where you go where you want to know how to measure things. There's in the United Kingdom, it's called the National Physical Laboratory. In Germany, it's called the Physikalische Technische Bundesanstalt. And each of your countries has one of these laboratories that deals with measurement. And that's what I'm going to be talking about, is measurement. I'm also associated with the University of Maryland. And together, NIST and the University of Maryland have formed a place called the Joint Quantum Institute. And within that, I'm a member of the Laser Cooling and Trapping Group. Gretchen Campbell is the leader of that group, and these other people, Paulette, Trey Porto, Ian Spielman, Ida Tietzinger, Charles Clark, and Nicole Younger-Halpern, are the permanent members with whom it's a pleasure for me to interact on a daily basis. But most of the things I'm going to be talking about today don't have too much to do with what we do in the Laser Cooling and Trapping Group, which is make gases of atoms incredibly cold, down to temperatures of 1 nanokelvin, 1/1000th of a degree above absolute zero, or even colder. Instead, I'm going to be talking to you about the recent reforms of the International System of Units. And in that regard, I'm also representing the International Union of Pure and Applied Physics, because I'm a member of the commission that has to do with units and measurement, and I'm spreading the word about this reform that has taken place. So, what is the nature of this reform? Well, what I claim is that we have recently undergone a real revolution in our system of units. It was the French Revolution that brought us the metric system in the first place at the end of the 18th century. And now, on the 20th of May of 2019, just a little more than 2 years ago, we've had another revolution. And the nature of that revolution is that the modern metric system, what is officially known as the International System of Units, or the Système International d'Unité, the SI. That system has been changed so that all of the base units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, these are the units in which we measure everything. Today, every one of those base units is defined by defining a constant of nature. Now, in order to understand how it's possible, what it even means to define a unit by defining a constant of nature, I'd like to tell you a story that I am calling, with apologies to the late, great Stephen Hawking, A Brief History of Time. Traditionally, the measure of time is the second, and a second was originally defined to be the length of a day divided by 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute, so that a second was one day divided by 86,400. The trouble with that definition, which was a very convenient and very clear definition, the trouble is that by about 1900, people realized that the day was not constant. The mean solar day, for one thing, changes throughout the year, but that really wasn't the problem. The idea of making it be the average solar day meant that it was averaged over a year, but people realized that it was changing not just because the Earth was going around the sun, but because of things like the tides. The tides represented a friction force on the Earth, and that was slowing the Earth down. Every time there was an earthquake, that would redistribute the mass of the Earth, and that would change the rotation rate. And by 1900, it was clear that that sort of thing was going on. There were mechanical clocks that were good enough to tell this. And as time went on, people developed even better clocks. The best clocks then and today are atomic clocks. Here's a picture of the very first one. It was at the National Bureau of Standards, which was the predecessor to NIST, where I work now. It turns out that that first atomic clock wasn't really even an atomic clock. It was a molecular clock, but it wasn't too much long. They redefined the second to be a fraction of the year 1900. What were they thinking? It's true that the year 1900 never changes, but it's not exactly easy to measure it today. Now, astronomers are very good at extrapolating, and so it wasn't a completely useless definition, but people realized this was not a very convenient way of defining time when we had atomic clocks that could keep really good time. And so in 1967 and 1968, the International Conference on Weights and Measures adopted a new definition of time, and that definition was that 1 second is equal to 9,192,631,770 cycles of the
Hi all. Well, I'm very sorry we are having some technical problems, but I think we have fixed all of them. That's the drawbacks of the hybrid edition. Okay, we all will be willing to be here in person in Salamanca, but well, this is one of the drawbacks. Okay, we are really sorry. We are going to go back to the exciting talk by Bill. We are seeing that you are in the platform, you are in the virtual venue. You can see there in the auditorium. So please, as I said, we are really sorry. We are going to continue with Bill's talk. So Bill, sorry about that. Again, the floor is yours.
Okay, so they tell me that we probably lost the connection somewhere around the beginning of talking about length. So I'll start there and maybe go a little faster in case it wasn't all lost. But we need to get to the end. So let's talk about length. Length was really important because length was necessary for commerce and for construction. But the original approach to length was that the human body was the standard of length, which was great because you always had your standard with you, but it varied from one person to another. And this was really annoying. So one approach was to make the standard of length the length of a particular person's body. Usually it was the king, the pharaoh in the case of ancient Egypt. And in ancient Egypt, they defined what they called a royal cubit. It was based on the length of the pharaoh's forearm. But it wasn't convenient to always have the pharaoh around. So they made an artifact, a piece of stone that was the length of the pharaoh's forearm. And they used that to do things like build the pyramids. In fact, they used a wooden secondary standard that was calibrated against the stone standard. And they were so serious about the metrology that they instituted the death penalty if you didn't calibrate your secondary standard. And the result was the pyramids were really well made. Well, this idea of having artifacts was widely applied throughout Europe in the Middle Ages. Here is one of those artifacts in the city of Regensburg, and it looks like a very nice long fathom compared to the arm span of this tourist. The trouble was that if you went into the surrounding towns, you would get a different value for how long a fathom was. And so the French revolutionaries wanted to fix this problem of inconsistency. And they came up with the idea of basing a new unit that they call the meter on the size of the Earth, something that would be universally available to everyone. The meter was 1/10,000,000th of the distance between the pole and the equator along a meridian that went through Paris. Now, how do you find out how long that is? They sent out surveying teams to survey the distance between Barcelona in the south and Dunkirk in the north. Measuring in the old units, they came back after several years of work, during which they were constantly being thrown in jail because people didn't know why these people were showing up in their town with strange-looking instruments. But after several years, they came up with the result and reported the result of what a meter was in the old units. The trouble is that this wasn't very convenient because you can't spend 3 years remeasuring the Earth all the time. So what they did was, in contrast to what they'd hoped to do, which was to make something that was good for all time and for all people, they instead made an artifact, just like the ancient Egyptians. This rod here is a bar of platinum that was as close to the meter that they determined by their surveying as could be, and they deposited this in the archives of France in 1799. Metric system as their standard of measurement, and that they would make a new meter. And this new meter was a bar of platinum iridium, and the meter chosen to be as close as possible to the old meter of the archives, was the distance between two scratches on this bar of platinum iridium. That became, and was for many, many decades, the standard length for the entire world. Now, the problem with this standard was that at the same time that that standard was made, people had begun to understand that they could use the wave-like character of light to measure length. People had discovered that light was a wave and that you could interfere two light waves. You could interfere them constructively to make something that was more bright than either of the waves, or you could interfere them destructively in such a way as to make the intensity of the light small or even zero. And in this interferometer, one of the instruments that can be used to measure length and to interfere light, two beams of light, one beam that comes in here and bounces, and bounces off this mirror and comes back, and another one that gets reflected from this mirror, bounces off this mirror and comes back. The two beams combined here produce an interference pattern like this. When they interfere destructively, you get darkness. When they interfere constructively, you get light. And if you move this mirror by just 1/4 of light, which is about 1/5 of 1/1,000,000th of a meter, you change this from dark to light. And it's easy to see that difference. You can measure to a small fraction of what we call one fringe, the difference between a dark place and a light place. And so you had an instrument that could easily measure length to much better than 1/1,000,000th of a meter. You had a definition of length that was the distance between two scratches. Imagine looking at the scratch with a microscope. The resolution of the microscope is barely. So that meant that you could not use the definition of the meter to measure length as well as an interferometer using light could. So we had just the same situation that we had with time. We had a way of measuring things, in this case length, that was better than the very definition of that quantity to begin with. And so people started to use the wavelength of light as a kind of de facto definition. For decades, finally they changed the definition. In 1960, they said that the orange light that comes out of this lamp, when it's operating, it makes orange light. And the wavelength of that light was defined to be a certain fraction of a meter. A certain number of wavelengths of light was defined to be a meter. So this was just like what was done in the case of time. You went from an artifact, namely the rotation of the Earth, to the wavelength of, to the ticking of an atom. Here you went from an artifact, the Earth, then finally a metal artifact, and then the wavelength of light. But 1960 was the year the laser was invented. And soon people were making lasers that made light whose purity was much better than the light that comes from this lamp. And so people started using lasers as the length standard. And they were the de facto standard of length, even though the official standard of length was the wavelength of light coming from this apparatus. People were using this apparatus, a helium neon laser stabilized to a transition in molecular iodine, and everybody reported their measurements of length based on this kind of laser. So again, we had a situation where the definition was not as good as the technology that allowed people to measure length. So what did they do? Well, they had to redefine the meter again. And the obvious choice would have been to define the meter to be based on the wavelength of these lasers. That would have been the obvious thing to do. Fortunately, they did not do the obvious thing. What they did instead was to define the speed of light. The new definition of the meter, the one that was the definition after 1983, and is still today the definition. It is the length of path traveled by light in a certain fraction of a second. And this number, that is the fraction, the denominator, the fraction of a second, is the new definition of the speed of light. Because if you say that the meter is the length that light travels in a certain fraction of a second, you have defined the speed of light in the process of defining what you mean by a meter. Now, why was this done in 1983? Because people had learned how to measure the frequency of light. Light is an electromagnetic wave. It oscillates at a frequency of a few times 10 to the 14 cycles per second. And by 1983, we learned how to measure that frequency. So think about this. This is a universal relationship. The wavelength of light times its frequency is equal to the speed of light. It's always true. We've now defined the speed of light. We know how to measure the frequency. That means for any light, we immediately know what the wavelength is. And we can use that light in an interferometer to measure distances. And here's the beauty. Let's say somebody makes a better laser that has more pure light and will make better measurements of length. And they did do that. That's already incorporated into the definition. Let's say somebody figures out how to measure frequency better, and they did. It's already incorporated. We should never have to change the definition again. We went from an artifact to a constant of nature, an atom, a particular atom, krypton, to a fundamental constant of nature, the speed of light. And the beauty is that this way we should never have to change the definition again. Now, in 2019, that beauty, that brilliance of the definition of the meter by defining the speed of light has been brought to the definition of the kilogram and the ampere, the Kelvin, and the mole. Why was it necessary to do that, and how was it done? Well, that's the next story. But before we do that story, let's stop and see if there are any questions about length or about time.
Thanks so much, Bill. I don't think there are questions now about time and length. We have many questions. They're more general, so I think we can maybe continue.
We'll take plenty of time to deal with those questions at the end. And if people come up with questions about length and time, we'll be happy to deal with those as well. But we'll just give them a few more seconds just to read these questions if they're interested. Okay, so let's go on. How are we going to change the definition of the kilogram? And for that, we have a light history of mass. So as with everything else, in ancient times, it was artifacts. Here are a set of stones from Babylonia that were the mass standards for Babylon. And one of these stones is a shekel, which is a unit of mass that you may have heard of. But the problem was the same as we had with length. Artifacts changed from one place to another. And so the French revolutionaries, in the spirit of trying to make things universal, came up with a new standard of mass. They called it the kilogram, and the kilogram is the mass of 1 liter of water. And 1 liter is a cube that is 1/10 of a meter on a side. So whatever the mass of that cube of water is, that's a kilogram, according to the new French revolutionary definition. The trouble was that it wasn't very easy to measure out a liter of water. Water sticks to things, the meniscus isn't flat, the density of the water changes with temperature. When you try to weigh it, there's buoyancy due to the air because the density of water is not very high. So there's all sorts of problems. So they did what everybody else always did. They made an artifact. This is that artifact. It's called the kilogram of the archives. It was deposited in the archives in 1799. And this is me holding it when I was visiting the archives. It's made out of platinum, one of the densest materials there is, so the buoyancy correction is not very big. And you don't have to worry about uh, your standard being a liquid. There it is. It's a nice piece of metal, easy to use. And that became the standard on which the international kilogram was based. In 1875, the countries of the world who agreed to adopt the metric system decided that there should be a new kilogram. So they made a new kilogram in platinum iridium, made it to be the same mass as the international prototype of the kilogram. I'm sorry, as the previous kilogram of the archives. They made the international prototype of the kilogram to be the same mass as the kilogram of the archives. And there it is. You see, it's well protected under 3 different glass domes. And this became the standard of mass for the entire world, and was indeed continued to be the standard of mass until 2 years ago. It was the last artifact. Now think about this. It's the 21st century. The unit of mass is an artifact that was made in the 19th century, based on an object that was made in the 18th century. This is a scandalous idea that in modern times we're using 18th century technology. Think about this. If somebody handled it with their hands and left a fingerprint on the international prototype of the kilogram, all of you would lose weight. Now, nobody leaves fingerprints on the international prototype of the kilogram, but its mass is changing nevertheless. Here is a plot of the masses of a bunch of copies of the kilogram that were made at the same time in exactly the same way. They just picked the one that was closest to the old kilogram of the archives to be the international prototype of the kilogram. Nothing special about it. All these other ones are supposedly identical, and they're changing relative to the international prototype of the kilogram. And it seems they're almost all changing in the same direction. Now, if you think about it, you might think, well, maybe it's the international prototype of the kilogram that is changing, or they're all changing. But of course, the international prototype of the kilogram cannot change, because by law, it is always a kilogram. Well, this is just intolerable. We had to change that. And the way in which it was to be changed was to use the same beautiful approach that we used for the meter. To define the meter, we defined a fundamental constant of nature, the speed of light. So what are we going to define for the kilogram? Well, to talk about that, let me remind you of what I'm sure is the most famous equation in history, E equals mc squared. What does this mean? It means that the energy of an object is equal to the mass of that object times the square of the speed of light. Okay, here's another equation that is not quite as famous, but is going to be very useful. It says that the energy of a photon, a particle of light, is equal to the frequency of the light from which we draw that single particle of light times a constant that we call Planck's constant. So we can just think of Planck's constant as being the proportionality constant between energy and frequency. If we define Planck's constant, and if we combine this equation with that equation, then solve for the mass, what we find is that if we know the frequency of a photon, because we've already defined the speed of light, if we now define Planck's constant, then we know the mass. Now, what do I mean by the mass of the photon? Because photons don't have mass. What I mean is this. Remember, mass and energy, because of E equals mc squared. Let's say I have an object like a nucleus, and it emits a photon like a gamma ray, and I measure the frequency of that gamma ray here. Because I've defined C and because I will define H, it means I know the mass by which the nucleus changed. That, we could call that weighing a photon. Well, that's not what we do. This exercise is just to show you that you could imagine that defining Planck's constant is going to give you a mass unit. We don't weigh photons. I mean, we can weigh photons, we just can't do it well enough. Instead, we use an invention from this guy named Brian Kibble. And he invented an electromechanical device, which I'm going to show you right now, that can be used to define a kilogram if we define Planck's constant. So here is a movie that shows how it works. Now, first, I want you to remember how you weigh things. Traditionally, let's say you've got an unknown mass here. If you want to weigh it, then what you do is you put known masses on the other side of the balance until the balance balances. So you keep putting known masses onto this balance until it balances. And when it does, then you know that the weight of this, mass of this, is equal to the mass of these known ones. And you say you have weighed your unknown mass. So you now know what the mass is. Now I want to invite you to think about a different way of doing this. Let's say that instead of having masses on this side, we have instead a coil of wire here and some magnets. And when you have a coil of wire with current in it, in a magnetic field, the magnetic field exerts a force on the wire. This is how motors work, right? But if you were to measure the current in this coil, and if you were to measure where the current went inside the wires, and if you measured the value of the magnetic field everywhere and the direction in which the magnetic field was pointing relative to the current in the wires, and you can't do all those things well enough, but if you could calculate the force on this coil of wire and then measure the acceleration of gravity, and that would tell you what the mass was, because the force on this side has to be equal to the force on this side. And so if you measure the acceleration, you get the mass. The trouble is that all those things that I said you needed to do, you can't do. So Kibble said, yes, but we can do something else. What Kibble said was, imagine that we take that coil of wire and that magnetic field, and we take the leads from that coil of wire, and instead of putting current in them, we connect it to a voltmeter. And then we move the coil of wire in the magnetic field. This will generate a voltage. This is how electrical generators work. They move wires in a magnetic field, and that generates a voltage, and you can use that to make electrical power. Same thing here. We call this part of the experiment the velocity mode because we're going to move this coil and measure the velocity using interferometers. We're going to measure the voltage using a voltmeter, which we can do very well. And those two measurements constitute the velocity mode of the experiment. That exact same coil in the exact same magnetic field has the other thing that we already did. We put current in it. We can measure the current all right. We can't tell where it goes. And we put it in a magnetic field, which we can't measure. And but all we do is we measure the current needed to balance out the force due to the unknown mass. And when we've got that, we've got everything we need. So look at this equation. This mass times gravity, that's the force that we're going to measure in the weighing mode on the mass side. We multiply that by the velocity that we get from the velocity mode. So we get this from the weighing mode and this one from the velocity mode. That has got to be equal to the current from the weighing mode times the voltage that we measure from the velocity mode. And the reason is that force times velocity is mechanical power and current times voltage is electrical power. And the two things have got to be equal in a proper system of units. So we can solve for the mass, and we find then that the mass is going to be equal to the current from the weighing mode times the voltage from the velocity mode divided by the acceleration of gravity times the velocity from the velocity mode. This is a new way of measuring mass. Now you might say, wait a minute, you said it was going to involve Planck's constant. I don't see Planck's constant here. And the reason it involves Planck's constant is we have a way of measuring voltage and we have a way of measuring current that involve Planck's constant. And it involves Planck's constant because of the quantum Hall effect from a guy named Klaus von Klitzing and the Josephson effect from a guy named Brian Josephson. So here is Brian Josephson. Here is Klaus von Klitzing. What Josephson taught us was that if you have two superconductors and you put them in proximity to each other with an insulator in between, and you put a voltage across it, that there's going to be an AC current that has a frequency of 2e/h, where E is the charge on the electron, H is Planck's constant, in hertz per volt. In other words, we've got something that converts frequency to voltage, and it involves Planck's constant and the charge on the electron. Von Klitzing taught us that in a certain configuration, that the ratio of voltage to current, which is resistance, would have be a certain fraction of Planck's constant divided by the square of the electric charge, and that's in ohms, the unit of resistance. So we've got 2e/h, we've got h/e squared. It turns out when you put it all in that the e's cancel out and the mass is proportional to Planck's constant. I know that was a little bit fast. We can discuss it in the questions if you like, but the point is, if we use this quantum way of measuring the current and the voltage, then we're going to get the mass in terms of Planck's constant. And if we define Planck's constant, then we got the mass in kilograms. And here's a picture of an actual balance at NIST, and it can make these measurements of the kilogram to a part in 10 to the 8th, which is better than the amount by which the kilogram seems to be changing from time to time because of whatever. We don't really know what causes it to change, but this is better than that. And here are some of the people who did that. They were so confident in their measurements that they tattooed the values of the fundamental constants onto their forearms. These people are really serious about the metrology. Okay, so why don't we stop here once more to see if there's any questions about mass or about time or length. I'll be happy to answer any of those questions before we go on to the end.
Thank you, Bill. Well, it's really interesting, and I would say a lot of people will be really wanted to go to the older way of the 18th century to see how they can lose weight with such a small thing. That's really great. Yeah, I think again we have a lot of questions, but from I think from a more general way, we've got a lot of discussion at the end, probably.
Okay, fine. So I just wanted to mention that this thing called a Kibble balance, this watt balance, this electrical way is not the only way of doing it. There's another way that involves first measuring the mass of a single atom in kilograms and then multiplying that up using a perfect crystal and a perfect sphere and counting how many atoms are in here. And that's another way of doing it, again, based on defining Planck's constant. And so laboratories all over the world were using one or the other of these methods for redefining the kilogram. And when they all agreed, then we finally decided we had finally done what the French revolutionaries had dreamed of. We were making a kilogram that was good for all time and for all people. And having decided that, the General Conference on Weights and Measures decided in Versailles in November of 2018 that they would change the definition of the kilogram and of the ampere, the Kelvin, and the mole. So they were all based on constants of nature. And 60 countries from all over the world unanimously agreed to change the definition. And after they did that, this was the movie that they showed in celebration.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
We have no special. Lo logramos.
Neyse Boli.
我们做到了.
Biz bundan ayrı olduk.
Proud om daar.
We wonnen жасадық. Het is ons gelukt.
We сделали это.
انتصرنا.
We gjorde det.
Hoe lang
Amerika, ja. My jsme to učinili.
Dokázali jsme to.
Congratulations.
축하합니다. Felicitazioni.
Congratulazioni.
Shatter le lavorisce.
Selamat sukses.
Parabéns.
Ongela. Omedetou.
Onneksi olkoon.
Mabruk. Aiko.
Félicitations. Congratulations.
So, anytime, anywhere, they really did have something good for all time, for all people. And you know, the idea that 60 countries of the world could get together and agree unanimously on anything is just amazing. And it gives me hope that maybe we'll be able to agree on other things as well. So the final part of the story is that the definition of the ampere is also changed. It used to be based on forces between wires, and now it's defined by defining the charge of the electron, a fundamental constant of nature. So the ampere is simply a certain number of electrons per second. And now that you've got both E and H defined, it means that 2E over H and H over E squared are defined, and that gives us voltage and resistance in units of fundamental constants. And then finally, we've got the mole. It used to be that the mole was the amount of substance that corresponded to the number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. But now we've just defined Avogadro's number. So a mole is just a number of stuff. And finally, the Kelvin. It used to be 1 over 273.16 of the triple point of water, just an arbitrarily chosen property of water. But now we've defined the Boltzmann constant. So I love this definition because it makes the definition of temperature based on our microscopic understanding of what temperature is. Boltzmann's constant times the temperature is the thermal energy of the microscopic constituents, the atoms and molecules that make up a substance. And now that's the way we've defined what we mean by temperature, by defining Boltzmann's constant. And so the French Revolution gave us the metric system. The Convention de Metre gave us an international agreement that the entire world would use the metric system. On the 20th of May, 2019, which was the anniversary of the signing of the Convention de Metre, we had the biggest revolution in measurement since the French Revolution. And now we can think of the idea of liberty leading the people as setting us free from the idea of artifact standards of measurement. We now have all these base units defined in terms of constants of nature. You can keep the SI on a wallet card that gives you the definition of each of these 7 quantities. It seems that we really have done what the French revolutionaries wanted to do, was to create something that was good for all time, for all people, except maybe for time itself. Because time is still tied to a specific atom. It's a constant of nature, but it's not a fundamental constant of nature. And if somebody comes up with another atom whose technology is better than the technology of cesium atoms, and they have, we're going to have to redefine what the second is. And the trouble is that it appears that we're going to again redefine the second in terms of a particular atom. And so it seems that we have got something that's good for all time and for all people, except for time itself. And as for the future of time, well, only time will tell. So thank you very much. And it's time for more questions.
Thank you very much, Bill. I think we will start with some of the questions that we have. I really enjoyed it. I think that you have shown us how the history, just shown us how the history of the system of units also tell us, like we've seen like with a camera, how technology has evolved during the last centuries, which is really great. It's really this topic in your career, in your research career?
Well, so now that's interesting. When I was an undergraduate, I was offered the opportunity to do some research by one of my professors. He was doing some research on something called electron spin resonance. It's sort of like nuclear magnetic resonance, except with electrons instead of nuclei. And he asked me if I wanted to get involved in this research. So I said, sure. So I did some research like that. And when I went to apply for graduate school, I had on my resume that I had done some things like that. And one of the people who looked at my application at MIT, named Dan Kleppner, one of the great names in atomic physics in the world, was doing experiments on magnetic resonance, precision measurement. I was just doing things trying to understand the line width, but he was making precision measurements, measuring things to a part in 10 to the 11th. Well, so he asked me would I like to join his group. So I said sure, and I did a precision measurement with him, several precision measurements, and it was on the basis of that that I was recruited to go to NIST to do more precision measurements. Okay, but there's more to the story. In the middle of my graduate student career, people started to manufacture tunable lasers. And so we bought some in the group, and people started to do experiments using these tunable lasers. Now, what does it mean to say it's tunable? It means you can change the frequency of the laser, its color, a little bit, so they could be tuned so that you could excite atoms. And that was the first time somebody could do that unless you were a laser expert and you built these things yourself. So people started to do experiments with atoms, and I'm still working on this magnetic resonance thing. So I go to Dan Kleppner and I say, you know, this laser thing really looks like it's interesting. I think that there's more of a future for lasers than there is for this magnetic resonance stuff. So I'd like to do an experiment on that too. And he said, sure. So we came up with an experiment, and I started doing an experiment on that. So I did two completely different things for my my thesis. The magnetic resonance, the precision measurement, got me the job. The other one got me the background so that I could start to investigate laser cooling. Because laser cooling, as you've seen, is good for precision measurement, because atomic clocks want to use laser-cooled atoms, so it's easier to measure them. So I started doing laser cooling in addition to the precision measurements. So the precision measurements led to this redefinition of the kilogram, and the laser cooling led to a new way of measuring time that other people have done, and it also led to the Nobel Prize.
Wow, marvelous, magnific, yeah. Very interesting view. So what will be the recommendation or the advice that you will give to those young students that are now like playing around, choosing between different topics? What would you recommend them?
Okay, well, there's a couple of recommendations. One that I think is the most important one, and that is never lose your curiosity. I think that the reason that most of you have gotten into the kind of studies that you're doing, regardless of whether they're in physics or in biology or in chemistry, or some of you are studying humanities, that the reason you're doing this is because you're curious to learn about these things. And this is the key thing that drives all research, is curiosity. And so I ask you, never lose that sense of curiosity. And the second piece of advice is very much like the first one. If you're looking around at a lot of different things that you might want to work on, choose the thing that fills you with wonder, the thing that that makes you say, oh yes, I really want to learn more about that. Choose the thing that is the most appealing to you, because not just because that means you're going to have fun, but that's the thing you're really going to work on that's going to make a difference. So there are just so many things around that are so fascinating. If I think about the way biology has changed during my lifetime, when I was a kid, biology was all about memorizing what the names of plants and animals were and where they fit into the phylum and the order and the genus and the species. And today, it's all about the molecular biology, how these things have evolved in the DNA, and how we can see their evolution written into their DNA. It's just amazing to me how much biology has changed. Or take physics. When I was a kid, there were no lasers. And lasers have completely changed the way we do atomic physics. They've changed how we do condensed matter physics. And there may soon come a time when they change how we do nuclear physics. And then think about this. Gravity waves were just a dream, something that ought to come out of Einstein's equations, but nobody could imagine we would ever see them. And now we see gravity waves all the time, and we learn new things about cosmological objects every time we see a good gravity wave. Things are changing so fast. New things are coming out so fast that it just seems to me that the menu of things that you might choose to work on is so wonderful and so fascinating. Choose the thing that gives you joy.
Yeah, completely agree. And yeah, talking about these new things, we've seen that in this contest, these young scientists, they came up with really surprising ideas and also with surprising questions here today. Like, for example, we have this, let's dream a little bit. Do you think time travel is possible? Will it be possible at some time?
Well, okay. So first of all, this is not my area of expertise, but let me tell you a story. I was standing right next to Stephen Hawking when somebody asked Stephen Hawking this question. And now sadly, Stephen Hawking has passed away, but when Stephen Hawking would answer a question at this point in his life, he was in a wheelchair and he was using a computer interface that allowed him to compose the answer that would then be spoken by the computer. So his answer was, well, it would be nice to have time travel, but I've never met anyone who came from the future, so I don't think so. So then, the questioner, you see, Hawking answered the question as if it wasn't really a serious question. But then the questioner said, but, I understand that if you get a large enough concentration of mass, like from a black hole, but it's a negative energy, and I get the curvature of space big enough, then it might be possible to create a wormhole. So now Hawking realizes, okay, this guy is a serious questioner. And so he gives a more serious answer to the question. He says, yes, these things are intriguing, but the difficulty in achieving the kinds of conditions necessary in order to create the kind of structure of space-time that might allow you to go back in time by a fraction of a microsecond are so difficult that from a practical point of view, you can just forget it. So that's Hawking's answer.
Okay, great. Let me connect this question with another question. So now let's imagine we can travel in time. And if you have the chance, what would you say to yourself when you were beginning your scientific career?
Yeah. Okay. So there's a couple of things that I might give as advice to my younger self. And I think it's still good advice. And that is, don't pay too much attention to what people say who think they know things.
Interesting.
Use your own brain to formulate questions that other people think are already answered, or don't necessarily take other people's advice for what you should do. So let me give a couple of examples. Probably the most important example is from my own scientific career and what people said about laser cooling. So when I didn't invent the idea of laser cooling. It was invented by people like Hensch and Shallow and Wineland and Daymelt. By the way, all those four people got Nobel Prizes for something else. Okay, so it gives you some idea of the quality of these people, that it wasn't laser cooling was not the most important thing that they did. They did other things that were even more important than that. So they came up with the ideas. What my group was able to do was to bring it into reality, was to actually make it happen. But the way in which those guys thought about laser cooling resulted in a relatively simple calculation for how cold you could get stuff. And everybody believed that this was an absolute limit to how cold you could get stuff. So when we first did laser cooling and started to measure the temperature, it was very hard to measure the temperature, and we got just what everybody expected for the measurement. And then we started to measure some other things, some other features about these laser cooled atoms that were easier to measure, but that people hadn't spent as much time thinking about. We spent some time thinking about them and we measured them. And it didn't work out at all. It was not the way the theory predicted at all. And I remember going to one of these theorists and I said, you know, if the temperature were lower than what the theory predicts, it could help explain some of this other stuff. Is there any way that that's possible? And he said, absolutely not. There's no way that's possible. This is the temperature. It can't possibly be lower than that. I said, oh, okay. So a few months later, we decided, okay, let's measure the temperature really well. And it was very much lower than what the theory said was the lowest possible temperature. And that meant that they didn't understand anything. And so it didn't take too long, once we got a really solid experimental result that people would believe. You know, it's one thing to say, oh, I measured the temperature and it's a whole lot lower. I mean, we're not talking about 10% lower. The first measurements was a factor of 6 lower. And eventually we got to a factor of 200 lower than what the theory said was possible. This was no small effect. This is a huge effect. So it's one thing to say that, it's another thing to get people to believe you. So we had to make sure that the experiments were really, really well done. We did a bunch of different kinds of experiments and described in detail how we did that. And then finally people believed us. And so then they started to figure out what could be wrong about our theoretical understanding. So they figured that out. We got even colder as a result of them figuring out what was going on, and it just changed everything. And so, first of all, we were slowed down by believing that people knew what they were talking about. And if we had continued to believe what people were talking about, we wouldn't have gotten anywhere. So it's really important to keep an open mind about what people think they believe. Now, you know, if you're questioning conservation of energy or something like that, well, or, you know, or the formulation of special relativity, these have been pretty well tested, and you're going to have to come up with some really good reasons for why it's not true. I'm not saying you shouldn't think about that, and I'm really happy that there are some people who are still thinking about whether special relativity is right, whether general relativity is right. It's probably not. There's probably something wrong with general relativity. We just haven't figured it out yet. So it's important to work on those things. But a lot of the other things that people take as being the standard way of thinking about things, uh, just don't take it too seriously. Keep an open mind about whether there might be something different. Another thing that I remember from my youth, when I first went to college, so this is undergraduate, I'm 17 years old. And so same age as a lot of you people, right? And I went to a small college where my sister was already a student. Okay, so my older sister, very smart woman. I was always coming up behind her, and the teachers are always expecting me to be like her, right? And she was a French major, and I was a physics major. Now, in this college, we were required to learn and become competent in a foreign language. And there were two ways you could prove that you could do that. One was you could take a test and show that you were competent. And the other one was you could take a class and finish a certain level of class, and you'd satisfy the, well, my language was French, like my sister. So I took the test and I passed it. So I'm done, right? So now the chairman of the French department comes to me. So he knows my sister, and he figures, here's her brother. And he says, oh, this is wonderful. Now you've passed this test. Now you're going to want to take the next class in French. Now, this is a class that's normally taken by third-year students, okay? And I'm a first-year student, right? And because I'm an idiot, because I'm only 17 years old, and this guy is the chairman of the department, I say, sure. What I should have done, of course, was said, well, thank you very much. That's very kind of you to think of me in this way. But I just don't have time because I have all these physics classes to take, and I have calculus, and, I've got to learn about differential equations. And, so, but instead I said, sure. So I go into this class, and there's all these older students, and the professor is lecturing in French. Well, I'd never experienced that before. It was all just, conjugating verbs and stuff like that. So I'm totally lost. And first test, I got a terrible mark. Now, if I'd had any brains, I would have said, okay, this shows this is not the thing for me. Let me just drop this course and I'll concentrate on my physics. But no. I said, I'm going to work really hard and I'm going to do better. So I did, and I got an A in the course.
Great.
And, I wasted a lot of time, but maybe not. Maybe I didn't waste time, because later in my life, I spent a year in France in the laboratory of Claude Cohen-Tanucci. And I insisted that we always spoke French. I mean, everybody in the lab spoke perfect English. But I figure we are in a laboratory in France, we should speak French. And I really think that the relationship that I formed with my French colleagues was a really important part of my scientific education. And we learned a lot of stuff. And so maybe the whole thing about listening to this old guy that I should take French, maybe it wasn't so stupid, but it sure seemed like it was a stupid thing for me to do back at the time. So anyway, there's two stories with different answers.
Perfect example. So thank you very much for sharing them with us. Let me go to a quick question just came out. They say there are still countries using ounce, pound, and miles. And they say that today Great Britain announced that Great Britain returns to ounce and pound. What do you think? Isn't this crazy that science uses metric system and society uses imperial system?
Yes, I do think it's crazy. And I didn't hear this about Great Britain. Great Britain has been a little bit of, a split personality about this. They officially changed to the metric system for general use some time ago, but they kept things like if you go into a pub, you order a pint of beer, not a half a liter. And the pint isn't even the same pint as you have in the US. So it's a little bit crazy. If you go on the autoroute in the UK, it'll tell you how far it is to the next town in miles, not in kilometers, but they abbreviate miles as M, which is, of course, the proper international abbreviation for meters. So it's always been a little crazy in the UK, and I'm very sorry to hear if they're actually changing back. It's a terrible thing. People often ask me, why is the United States so crazy? But let me point out that the United States was one of the original signers of the Convention de Mètre. We have been metric since the 19th century. But the questioner was very correct to say that there's a difference between what we do scientifically and what we do as a society. So the United States is metric legally. We don't have any inch standard anywhere. We don't have any pound standard anywhere. The inch is defined in terms of the meter. The pound is defined in terms of the kilogram. So legally, everything is metric. But we have this sociological phenomenon that we still use what some people call the English or the imperial system. It's not really the imperial system in the US because our gallons and our pints aren't the same as the imperial gallon. But anyway, slowly in the US, we're changing. If you go to a grocery store and buy a plastic bottle of soft drink, of soda, it'll be metric. But if you buy milk, it'll be English.
Wow.
So, why is that? But if you buy your soda in a can, like this one, it'll be English, not metric. But if you buy a car or a bicycle, the screws will be metric. So,
what's the solution then?
One solution is it'll just slowly fix itself. But I think that what it requires is a political leader who has enough courage to say, look, this is silly. We are losing money in the international market because of making stuff that can't be used in the rest of the world. We're just going to change now. We're not going to any longer tell you what the speed limit is in miles per hour and in kilometers per hour in small print. All the signs are going to be in kilometers only. We're going to report the weather only in Celsius. Everything in the supermarket is going to be sold in kilograms and in and in 3 months everybody would be fine. Everybody would complain, and then in 3 months everything would be just fine. But nobody has that kind of political courage.
We are depending on politics.
So maybe just little by little it'll change, but it's going to take a long time. People talk about metric things all the time now because they see them in the stores, and they drive and ride on vehicles that are metric. But we still only report the weather in Fahrenheit, and so maybe if we start selling milk in liters instead of quarts, it'll be fine. I can see how wonderful it would be. Somebody would say, but if you buy our milk, you get a liter for the same price that the other guys are selling a quart. That would be a great advertising thing, but nobody's doing that.
Definitely. Okay, I think we are running out of time, but thank you so much for staying long due to the technical problems. One last question. What is the best and worst thing about winning the Nobel Prize?
Well, okay. So one of the best things was that people gave me some more money to do research. So I was able to hire some more people. And the important thing is to hire people who are smarter than you are. So this is great. You get some young people who are really smart, and then we can just have more fun. And I could buy some more equipment, get some more lasers, and so that's a really good part. The bad part is that people think, and it was Feynman who said this, people now think you know something about everything. And people will ask you questions about life and
Time travel.
well, time travel is sort of a scientific thing, but about how you should choose what you want to do with your life. What do I know? I mean, my advice isn't any better than anybody else who might give you advice about that sort of thing. And that's part of why I said be careful about listening to advice about life from people. But now let me add one more thing. You asked me the best and the worst. Let me also ask you the most unexpected thing. And that was that I got to meet famous people. And you might say, well, wait a minute, you're famous. No. If you go out on the street and ask anybody who won the Nobel Prize in Physics this year, they won't even be able to tell you that, okay? Unless you happen to get a physicist. If you were to ask them who won the Nobel Prize in 1997, then of course they wouldn't know. And if you were to ask, what is Bill Phillips famous for? They would tell you, oh, he's the guy who wrote that book about bodybuilding, right? The one who is on and because there is a guy named Bill Phillips who is a bodybuilder, and he's written a whole lot of books with his picture, with the big muscles on that's all you would get if they even knew that, which isn't likely unless you asked a particular demographic in the United States. You might find some people who knew that Bill Phillips, but nobody would know me. But I have actually had dinner sitting next to the President of the United States. I have become friendly with people who are household names that everyone in the United States knows. So that was not something that I anticipated would be part of the Nobel Prize.
Okay, Bill. Well, thank you very much. I think all of us, we have enjoyed a lot of your talk and your discussion and your excellent advices for our young scientists. And I'm really sure they've enjoyed this. And again, we are really, really happy to have you here. Thanks again. And we are apologize again for the technical problems for everybody. And thanks again. With this, I close the session. Bill, if you want to add.
It's been a pleasure for me. And just remember that part of my advice is be careful about taking advice.
Okay, Bill, thank you so much. Thanks to all people attending. And okay, bye-bye.
Bye-bye.